Yeah. Okay, so we learned from yesterday that definite integrals it's area related. Okay, area related. But we do know that sometimes if your region is living below the x-axis, then we're going to get some negative values accumulated in our answer. So this theorem is called the average value theorem. Also involves area, but the bigger idea here is that this is a mean value theorem for integrals. So if you think about mean value theorem from first semester was where if we have a curve and whatever slope we find between two given endpoints, that slope is guaranteed to live somewhere along that interval. Right, so there's a slope of -1/2, and this curve is smooth, then there must be a slope of -1/2 somewhere along the graph. Average value theorem is not guaranteeing a height. Sorry, it's not guaranteeing a slope. Rather, it's guaranteeing a specific height. Okay, so basically, we're saying that we can guarantee a specific height over the course of that interval. Okay, but let me kind of back up a little bit and talk a bit about what this theorem is doing. Okay. If we think about area of a rectangle, what's the formula for area of a rectangle? Area is width times height. Okay. Now let's say I wanted to solve for height. Right. So if I want to solve for height, how would you rearrange this equation to solve for height? Yep. Height equals area divided by the width. Okay. So really, this formula is really a rearranging of the area rectangle. Oh, sorry, area formula for a rectangle. Okay. So we know that this. Thank you. We know that this integral is area related, right? And the b minus a is really the width. And so area divided by the width is equal to the height. Now, this is 1 over b minus a. I'm multiplying by 1 over b minus a, but it's really same thing as saying this divided by b minus a, right? So area divided by width equals the height. So what we're doing is we're finding the average height across this curve. So if I were to take all these different heights, all these infinitely many different heights, and if I were to average them all, this formula would give me the average height. Okay. So also, in other words, if there was a rectangle that contained the area of this region, then the height of that rectangle would be f of c. Okay, so let me read this statement here. There exists a rectangle such that the area of the rectangle is same as the area under the curve, and f of c is the height of that rectangle. Okay, or in other words, it's also the average height across all the different heights in that interval. Okay, and the way we find it is we involve definite integral, and then we do divided by b minus a, which it feels simpler just to push that fraction out. Instead of divided by, we do multiply by the fractional value. But it's really area divided by the width equals the height. Okay, so let's try example 1. Example 1 says find the average value, in other words, find the average height across all the heights on x squared plus 1 from on the interval from 2 to 5. Okay, so let me write the formula, and we're going to apply the formula here. Okay, so what are my A and B values? 2 and 5, right? Yep. So let's replace those. A is the left or lower bound, and B is the right or upper bound. So f of c equals 1 over what? Yeah, 1 over 3, or I'll put 5 minus 2 to begin with, but eventually it will be 3, from 2 to 5 of x squared plus 1. Okay, what do you think our next step is? Good, find the antiderivative. Now, I think this is the type of problem that I see a lot of students wanting to involve the 5 and 2 directly with this expression. And maybe the reason why is because, I feel like some students, they go through this process and they feel like they've already done the calculus and they're now ready to plug in the value. So this is just the setup, right? But that 5 and 2 is staring back at you, and I think a lot of students want to just go ahead and involve that with the x squared plus 1, but it's not ready. Okay, we got to do the indefinite integral first before the 5 and 2 has any impact. The 5 and 2 is never going to look at whatever you see here. Okay, we got to transform this. Okay. Now, what I like to also do is I like to leave this fractional value till the end. You can distribute that 1/3 through, but then if you do, there's just more fractional values to deal with. I typically like to wait until the end to deal with that fraction. So I'm just going to leave that 1/3 alone. Well, let me rewrite it just so we can see that it is 1/3. And I'll come back to it. So I want to make sure I don't forget about that 1/3. But I'm going to ignore it for now and just focus my attention on that x squared plus 1. So both terms are set up and ready for power rule. X squared plus 1 becomes what? X to the third over 3 plus x. Now the 2 and 5 are ready to be used. Okay, what gets inserted first? Always the upper bound. Yep, upper bound first. Minus parentheses. Now we're ready for the lower bound. Okay, 2 gets inserted into the expression. All right, let me just clean all this up here. This is going to end up giving us 126 over 3, but are we done? Okay, we still have to multiply by what? 1/3. So basically, we have the area component, but we're trying to find the height. So area, we need to divide by the width. Area divided by the width equals the height. So the average height is 1/3 times 126 over 3. Which reduces to be 14. So the average height along this x squared plus 1, 2 to 5, okay, is 14. So if I were to look at all the heights here, the average height is going to be 14. Okay, so the formula feels complicated, but I just want us to just, like if we understand the concept of, oh, we're just rearranging the rectangle formula, area of a rectangle formula, then it feels a little bit more familiar. Okay, all right, so that's part A. Any questions there? We found the average height. But now part B says find the C value. Okay, so what does the C value mean? We found the average height. So the average height is basically saying we're guaranteed that this graph is going to hit that average height somewhere along the curve. Okay. But where does that occur? So we have the y value. We know that there is a y value of 14 somewhere along the curve, but we're trying to figure out where that y value is. Okay. Or basically we want to find the x value. So let's say we know where 14 is. We're trying to figure out that x value. So how do you think we can find that x value if we know the y value of the function? Good. So we know what the y value is 14, and we're just going to use the function to figure out the x. Exactly, right? So we've done the hard part. Now we're just basically finding the order pair, right? We have the y value. What's the x value? Okay. $14 is our y value. And we're just going to solve for x. Now, when I take the square root, what's going to happen? What's going to appear in front? Plus or minus. But what's wrong with one of those x values? It's not between the interval, right? So kind of like mean value theorem and Rolle's theorem from first semester. If we find a location that's not part of the interval, then we remove it, right? It's not part of our domain. So our c value is just going to be positive square root of 13. And square root of 13 is between 2 and 5. It's around like close to 4, right? 3.6, but we just know that. Right. So the location where the graph is going to hit that y value of 14 is at root 13. So again, average value theorem, I don't think is too difficult because really you're just doing doing power rule, evaluating the upper and lower bound, and just keeping track of that width. So that width component is something you're really just including. That's the only new thing from previous problems. But for some reason, when students get this complicated of a setup, they tend to want to forget about the power rule and start inserting values into the expression. So just be careful of that. I do see that a lot. So just be aware that I can't work the bounds with what I see in front of me. I got to transform that expression first before the bound has any use. Okay, page 6. Okay, so we'll practice with that a little bit, but I do want to talk about the second concept that I want to go over, and that's the second fundamental theorem of calculus. Okay, so the first theorem is just evaluating upper and lower bound with an integral. Okay, the second theorem is really exploring that relationship between derivatives and integrals, that they have a way of undoing and canceling each other out. Okay, so the big idea here is if I take the integral of a derivative of a function, those two operations will just kind of cancel each other out. Okay, or if I take the derivative of an integral, they're also going to cancel each other out. So think of it as I'm adding something and subtracting something. You know that they're going to wipe each other out. Okay, so to recap, we've covered indefinite general integrals. This is an area finding function. This is where the integral with no bounds. But then we've also done definite integrals, finding the area between two values. And this, we take the power rule and plug in upper and lower bound. But now there's also a function that's the integral itself. So instead of going from a constant to another constant, we're going from a constant to a moving value of x. And we don't have to worry so much about, visualizing this. We just have to know how to work or deal with a problem that has a variable that has an integral as part of its function. Okay, so this is very important here. Second theorem of calculus. Sometimes I would abbreviate it SFTC, second fundamental theorem of calculus. So this applies the concept that a derivative and integral are basically inverse operations of each other. So big picture here first. The big picture here is, let's say I asked you to find the integral of f of x dx. Okay. And then after that, I asked you to take the derivative of that. What do you think I'm going to end up with? Good. Okay, that's the big idea here, right? If I take the antiderivative of something and then turn around and took the derivative, I'm back to where I started, right? Because I'm basically doing an operation and then undoing it, right? So if you understand that concept, then the big picture is that these two operations, it's almost like as if nothing happened because I'm back to where I started, okay? So if you understand that concept, that's kind of like our starting point. However, if there's any variables involved, then the integral and derivative process is largely going to wipe each other out, but that variable is going to end up there's going to be some remnant of that variable impacted by these two operations. Okay, so the big picture is that largely nothing is going to change, but that variable is going to have its impact from the two operations. Okay, so here is what's going to happen. So if I take the derivative of an integral, that upper bound is going to get inserted into the function. So it's almost like as if the function, nothing happens to the functions, but that variable does get inserted into the function. And the derivative does have a impact on that variable. So there's also a times p prime. But largely, this function is not going to change. Okay? There's just a little bit of adjustment we have to make with that upper bound. Okay? But it's still a shortcut because we're not doing the full integral and full derivative. We're just jumping to the end. Okay, so let me kind of show us what I mean by that. This looks complicated, but I want us to just feel like, oh, I'm just skipping to the end because I'm not doing both operations because I know I'm going to end up where I started. Okay, so my starting function is the square root of t squared plus 4. There's an integral and derivative operation. These two are going to cancel each other out. Okay, however, the upper bound is going to get inserted into the function. So if I were to insert that x into the expression, what would that look like? Square root of what? Yep, x squared plus 4. All I'm doing is I'm just replacing this t variable with this upper bound variable. Okay, so I took care of this f of p of x. So I've taken my function, replaced it with x. Now I need to multiply by the upper bound's derivative. So what's x's derivative? Times 1, right? So it looks like it's almost like as if nothing's changed. So all this mess, we can just kind of ignore both those operations because we know these will cancel each other out, and we can just jump to the end. Does that process make sense? Okay, so part B, there's an integral, there's a derivative. They're both operating on the same function, but it's almost like I'm adding and subtracting something, right? Not much is going to change, but this variable does have an impact. Okay. All right, so what is that going to turn that expression into? Replace the t with x squared times, okay, the derivative does have an impact, times what? Times 2x. So if we were to go through all the trouble of taking the integral, power rule, plugging upper and lower bound, clean up, find the derivative, this is what we would get. But we can save a lot of time because we know that we're just coming back to where we started. Yes. Yes. Yes, it goes away because this, imagine taking the integral and it's in terms of t, right? But then all the t gets replaced with x. So all those original variables go away. So here's an example. It's not quite this problem, but imagine if I had a problem that looked like this. Okay, so I go through power rule. This gives me t squared over 2 plus t. And I go from 3 to x squared. Okay, upper bound in, I get x to the 4th over 2 plus x squared minus 3 squared over 2 plus 3. So you see that all the t's goes away. I'm just left with x's. Also, what do you notice about this problem that has no impact whatsoever? The lower bound, okay. Any idea why this lower bound has no impact? It's a constant, okay. What else? Because if I went through this process, I'm going to end up with a number. But there's a what in front of this. There's a derivative. And what's the derivative of a constant? It's going to be what? It's 0. So this integral process will produce a number, but then that derivative is going to wipe whatever constant is left to be 0. So if we're going through this process, if we see any constants, we can ignore it because it's just going to disappear down the road. Okay, part C. Derivative of a definite integral. We know these two operations will cancel each other out. I don't have to go through power rule with this expression. I can kind of leave this alone. But upper bound gets inserted, so I get square root of x squared minus 1 times 2x. Okay. What do you notice about parts B and C? They're the same, even though the lower bound is different, right? That kind of shows you that the lower bound has no impact if it's a different constant. Okay, part D. Thank you. Part D, what do you notice is different about part D? Yeah, the bounds are flipped, and we want the upper bound to be the variable. So what can I do to make it look more like what we've seen? Okay, we can do it with the bounds. Can we make them swap places? Yes, but what adjustment do we have to make? Negative, good. So I'm going to rewrite this problem. Remember, you can always flip the bounds, but if you flip the bounds, you're changing the problem. So if I want to balance that change, I'm going to have to include a negative in my expression. Okay, so now it looks just like the previous problems. Again, derivative is on top of an integral, on top of an expression. We know that this expression is not going to change much. Okay, however, the upper bound does have an impact. So what gets produced? So that takes care of this f of p of x times this derivative does have an impact on that 3x. That 3x becomes what? 3, good, 3. Okay, so f of p of x times p prime of x. Okay, so I can leave it like this, or I can write it as a fraction. Okay, question so far? Okay, part E, what's different? They're both what? Variables. So if they're both variables, that means they're both going to produce something that we got to keep track of. So for this rule number 2, I have an adapted rule for upper and lower bound that are both variables. And basically, we do the same thing between the upper and lower bound. Upper bound first, then lower bound, and we just insert a minus in between. So we do the same thing that we do with the upper bound. We just do it twice, and then we put a minus in between. Okay. All right, so upper bound first. X squared, and for that expression, I get 2 x squared plus 3 times what? Times what? What's x squared's derivative? 2x. Okay. So minus. Okay. Now I got to do the same thing with the lower bound. Okay. Lower bound into the expression, I get 2x plus 3 times 1. Okay, so not much of an impact, but we still have something there. Okay, so do some cleanup here, distribute that 2x through. Careful, this minus sign is going to impact both my expressions, so we always want to get into a habit of putting parentheses after a minus sign anytime we have an integral or anything related to integral notation or definite integrals. Okay, any questions there? Right, so let's try the two problems that you guys picked up. And first, let's do an average value theorem. Here's the formula. First thing you do, insert the expression into the formula, and then start cleaning up, right? Power rule, antiderivative, then work in the bounds, and then work in the fraction. Yeah. So, (32/3). So once you set up your formula, power rule for your antiderivative, work the bounds in, but make sure that you understand what you've achieved is only the height, sorry, is the area. We still got to make sure we involve the width component. So make sure you multiply by that 1/4. Then you have your average height or average value. The upper bound minus the lower. Then we do the one thing. So it's that would be minus something. Anybody have any questions about this process? Taking the antiderivative and working the bounds, right? Upper bound gets inserted for all the x's, then put a minus sign, big parentheses, and then apply the same process for the lower bound. And after all that mess, you'll get 32/3 times 1/4, which will give us 8/3. Okay. So now we have the average value. How do we find the C value? Yeah, so basically your average value is your Y value. Right? So I know the average height of my graph. Now I want to find the location where that exists. So replace 8/3 in for the Y of your original function, and then solve for X. And make sure you're using the original function, you're not using the antiderivative. Okay, we got to go back to the original graph. So 8/3 equals 4 minus x squared. Bring the x squared to the left side, subtract 8/3 from both sides. 4 minus 8/3, same thing as 12/3 minus 8/3, which is 4/3. Take the square roots, plus or minus square roots, and 2/√3 and -2/√3. They're both inside the interval from -2 to 2, so we can keep both locations. Yes, because both these decimal values are safely between -2 and 2. This part, if it is, it'll be easy to find, right? So I won't give you, or I will give you some help, right? So either, yeah, so you never have to worry about, trying to find messy value. Okay, any questions with average value theorem? Okay, let's try second fundamental theorem. That's on the back. Right. Just make sure we're on the same page here. What initial adjustment should we start?
Oh, flipping.
Yeah, let's get the bounds matched up with the rule that we want to use, right? Let's get the variable up top, constant below. So then once you have that, make sure you adjust with the negative, and then you can follow the rule. The rule just says, well, these two operations are going to cancel each other out. Upper bound gets inserted into the variable of my original expression, multiplied by the upper bound's derivative. So there's my initial adjustments. Okay, replace every t with what? 2x cubed. And then just multiply by upper bound's derivative. 2x cubed is 6x squared. Just do a little bit more cleanup after this. Let's see here. Okay, let me just do, let's have us do two more of the second theorem. And hopefully you have enough space on this page where you can try these problems out. This is from the textbook here. Derivative signs. What's the signs?
Wait, this is my sense. Oh, this is what. I think you're saying the derivative or something. It's like because it's possible.
Okay, let's try this here. First thing we do is upper bound into the expression, which gives us what? Square root of sign. So we're done with that first portion. Now we have to multiply by the upper bound's derivative with sine's derivative.
Cosine.
So
Oh, this tangent.
okay. 91. Right. And the reason that we can go through and do minimal work on that square root of t is because we know these two operations are just largely going to undo each other. So this expression that you see is not going to change much. Okay. T gets replaced with x cubed. So x cubed squared becomes what? X to the right. Oh, the reason why we multiply those exponents because they're next to each other, right? It's not t squared times t cubed. In that case, we would add exponents, but this is t cubed squared. So we'll multiply and then multiply by the upper bound's derivative times sine x to the sixth times 3x. Yeah. All right, you guys have homework from the second part of 4.4. And tomorrow we'll do use substitution and we'll spend a couple days with use substitution as a big topic. All right, come get your phones.
Question, what is this? Because that's to show like people.
By the area, this is the antiderivative of this.
So it's fine. Yeah.
Basically. Remember, a depth integral is area related. It's area.
Uh-huh.
Yeah.
It's a really good conversation.
Okay. Good, thank
What
you.
about this one? Someone didn't do this.
Oh, and then
Oh, that's right.
also from the textbook,
If you put it right in.
so these problems as well.
Oh,
Just go through.
yeah.
Great.
Where I know, I was wouldn't it just be two X?
Yes, 2x squared, but then see that 2x there? I just did that 2x.
Oh, you just did it straight. Okay. And to clarify, when you're, if you're switching, you don't switch the sign of, you only switch the sign of that. So like the signs don't change when you flip them, only the function.
Yes, oh, you mean these don't change that, yeah. You're right.
Yeah.
You're just flipping the bounds, but bounds are not gonna change it. These the functions.
Okay. And then one more thing, so why did you multiply that every year?
Oh, because of this, if I have x cubed squared, if I have two exponents next to each other, I'm gonna do multiply.
I don't know.
But if I have this, x cubed times x squared, then I add exponents.
Oh. Can you go? Oh, this is. I don't want to talk about fun food. That would be.
These two.
Yeah.
No, we'll incorporate them into.
Like, that's pretty good. Because I mean, one from the.
Yes, actually, no.
Well, you're fine. I can't even sit back and look. It's all right. I'm gonna be just. Okay. On the board,